Okay, good morning everyone and welcome to the Big Tech Day 2025, our annual conference for science and technology enthusiasts. Also would like to welcome our guests who are joining us over Zoom. Hi, I hope you can hear us well. If anything happens, if there are any issues with video or audio, please let us know. We will always monitor the chat if something comes up. So for almost 2 decades now, TNG has hosted this event called the Big Tech Day that brings together experts from science and industry to discuss and talk about the latest groundbreaking research and transformative technologies. So we are very happy that this year, at the 18th iteration of the Big Tech Day, we're able to bring together 1,400 guests, 75 speakers, with 40 expert talks across 7 parallel tracks. So given the current technological landscape, of course, many of the talks today will be about AI, but we will also be hearing about the latest advances and applications in other fields, such as cloud or robotics. Also, you don't have to worry too much if talks that you're interested in are happening in parallel. The recordings of most talks will be made available afterwards on our Big Tech Day website. Right, and also to keep you refreshed and your energy levels up during the day, we will of course provide various snack and beverage stations across the venue. Similarly, there will also be lots of distributed lunch locations. So in case one place is too crowded for you, please find yourself another location. They're all marked on the site plan. You can find all information also on the website, of course. We guarantee that there's enough food for everyone. The tech industry is already competitive enough, so at least for today, you don't have to fight for the food. So in addition to the talks, we will also have exhibitions and showcases just down there in the main hall under the big LED cube. Most of them are interactive and also provided by our innovation hacking team, our in-house tech lab, so to say. It's a dedicated TNG space that offers our innovation hacking team the possibility to assess and creatively blend or hack together the latest tools, be it hardware or software, to push the boundaries of technology. So therefore, I'm very excited to introduce you to Daniel Hirsch and Lennart Schiefelbein, 2 members of our innovation hacking team and the speakers of today's talk. They will guide you from the basics of computer vision to the latest generative AI techniques such as Stable Diffusion, all the while providing visual live demos and also connections to real business use cases. Also want to note that we will not be answering questions during the talk, but we'll have instead a dedicated time slot after the talk to answer your questions from Zoom or from the room. So our first speaker is Daniel Hirsch. He's a software consultant at TNG who has already specialized in computer vision during his computer science studies at LMU in Munich. He has been with the Innovation Hacking Group since 4 years, where he created various AI showcases and also prototypes. Besides hacking on new showcases, Daniel has also successfully contributed to several client projects with his knowledge in AI and computer vision. That includes AI-assisted code migration, fine-tuning of image models, and further generative AI applications. Our second speaker, Lennart Schiefelbein, is a senior consultant at TNG Consulting with a background in mathematics. He has previously worked as a software developer for a smart home project and has now transitioned full-time to an internal role here at TNG. Besides his work in the innovation hacking team, where he works on reinforcement learning and computer vision, he also drives other AI topics such as benchmarking for large language models. So please give a warm welcome to our 2 speakers.
Yeah, thank you. So, can AI see you? This will be the question of today's talk, and the next 40 minutes will be all about computer vision and GenAI. But before we get started, let's talk a bit about us. So,
hi, I'm Daniel, and as Simon already introduced me, let's keep it short. Yeah, I'm part of the innovation hacking, which we'll explain later. And we want to mention, of course, our nice exhibition which we provided, and a lot of our presentation here has also some demos of some of the showcases, and you're free to join us afterwards to look at them in a live stage. But let's come to you, Lennart.
Yep, sorry. Yeah, I'm Lennart. As Simon already introduced me, I'm a senior consultant at TNG, and together with Daniel, I'm part of the innovation hacking at TNG, where we apply all kinds of new and fancy technology to build fun showcases, which you can check out. Can't mention that enough. And today, we'll show you how we do that and which technologies we apply from computer vision and GenAI to build these showcases. So let's get started.
But first, Leonard, your picture, is that really you? It kind of looks a bit old. Was it in high school, or when was the time you made this picture?
Well, it's like yesterday that I made it. It can't be that old.
I think you don't look that similar. And where are your shoulders even? I think we need to fix something here. So let's give you some shoulders. Better, right?
Yeah, a bit better. But what's that in the background? Is that a door or window?
My mistake. Let's remove that. But
yeah, that
now
looks much cleaner. Yeah.
it's still, I think there's something missing here, something a bit hairy. Let's give you maybe a little bit more facial hair. And what about a mustache? Is that okay?
Not sure. I'm not that mustache guy, I must admit.
You want some more?
Yeah, please.
Let's do a goatee.
I think that's even worse.
Then let's do a little bit more, maybe with some sideburns on the side.
Yeah.
Sorry.
Oh, actually, that looks fine.
No, sorry.
Close enough.
Yeah, we already spoiled it, so let's go to the next slide. Give you some more beard. I think now you may be a little bit looking similar than what we had before, but let's reimagine everything what we have seen before and put you in a whole new outfit. Is that better? I think that's a nice speaker photo, right?
Yeah. Well, I guess
we
I can go
we
with
will
it.
just take this one. Yeah, and what you have seen here is everything related to computer vision and GenAI. So computer vision itself is all around us, so it's ubiquitous. And if you look at every face filter, every scanner, every whatever you're touching with that has something to do with technology, you mainly use some kind of computer vision. And that's why I am fascinated about it, and I love doing things with it. And this way we want to show you today to use computer vision on your own and see what you can achieve with it. And to do this, we first have to, of course, look at how the computer or how the system understands computer vision. So in general, of course, you have an image, but the image you perceive is, of course, an image for you, but the computer doesn't know what an image is. So we have to make the computer know what the image is. And this is the topic to make the computer really see what's inside the image.
Mm-hmm. So now that Daniel had some fun with my profile picture, let's have some fun with Daniel's profile picture. So how does a computer actually see Daniel? And I guess most of you already know the answer. It's in pixels, of course. So picture elements, the way we can discretize an image in order to save it and make it understandable for a computer. That's the one thing. And the other thing, which is important to understand and to keep in mind, is RGB, the colors of a picture. So we can split each and every picture in 3 different channels, red, green, and blue, in order to represent the colors. And this gives rise to a representation as numbers. So images are nothing else than numbers. Matrices which have channels, one for each color, red, green, and blue, a width and a height. And this is actually really understandable and possible for a computer and gives us many possibilities to do, for example, artificial intelligence with it. And the first concept or the first model we will introduce are convolutional neural networks.
I mean, as we have an introductory talk, of course, we don't want to keep the mathematics too complicated here, but like a little bit of mathematics still in the beginning, so don't be worried. So we have this matrix, and what can we do with matrices? We can multiply them. And what we're actually doing in a convolutional neural network, we have this matrix with numbers, and we take another metric that is smaller. Of course, the mathematicians behind know that this will not be able to compute, but what we actually can do is take this and put it on top of the image in like a small part and only extract features patch by patch. So in this way, we only look at like something that is called the receptive field, to have like a small part that we're actually looking at and detect something inside of it. And this here on the right is called the kernel or filter that has the characteristics that this all kinds of letters you cannot, or Greek letters you see, are the parameters of the model. And these can be learned from the convolutional neural network, and this is the whole magic behind it. So what we're actually doing is taking this matrix, so you see here the 3 times 3 matrix, and sliding it over the image. And this way, we extract all kinds of information from the image, depending on what this matrix this matrix looks like. So, for example, if you have the kernel initialized with some specific numbers, you can be able to extract information like, sorry, like this, where you, maybe it's a bit too dark here, but where it detects edges. And for this to be happening, it's pretty simple. You have some things that has larger numbers on the one side and smaller numbers on the others, and you will see. I'm not a professor. I will not prove it here, but you will see that this will be able to detect edges in the image, and you could do this for all kinds of different characteristics you want. And this is the whole magic in convolutional neural networks. You will be able, depending on how the kernel is initialized or the kernel is trained from the model, what will happen in the end, this is the way what actually the features are of the model. So this could be edges, this could be coloring, this could be all kinds of lighting and stuff like this. And this is the magic of convolutional networks. And this is not only happening for like images that, or the resulting image here must not be the same size. You can also shrink the image if you don't slide 1 by 1, but maybe step over 2. So then the output size, because you're kind of summarizing all the items, you will get a smaller matrix out. And this way you can kind of shrink the network. Of course, there's a lot of different kind of operations that you need to do, but this is essentially what you can do with it. And you will not do it only once, you will do it a few times, and the convolutional neural network normally looks like this, or this is kind of a downsampling effect here. So you have image output layers that, or we call layers, like one layer at a time. We have output layers that are the same size, and we have output layers that have smaller size. And this way you can kind of compress the image itself, but you will learn these kind of filters. And the more filters you learn, the thicker here this is symbolized, because there it gets the characteristic form. And in the end, what you can do is you have like a small output that you can do kind of a lot of computer vision tasks with. And sorry, the remote doesn't work too well. What you can do, for example, if you have like an image of a dog, you compress this and you have some trained neural network. In the end, you can put this inside and maybe get a prediction that this is a dog. This can also be like a cat, and then you have like a classification, as we call it, that says, oh, I learned this looks like a cat. And this can also be, if we put in my picture, That is awesome, by the way. Put it in, and this says it's Daniel. Of course, we have to train. We skipped a lot of things here, but this is how this will work. And lastly, we can also, like if we have a classification, we can also switch it with something else. And then
Yeah, exactly. We have now seen how to shrink and descale and extract the features of an image such that we can get an information which simply says it's a dog, it's a cat, it's Daniel. What else we can do is we can also upsample this from this part, and we can make this space in which our information is bigger. And in fact, we can train this neural network in a way such that it returns the output. You might say this might be
this looks different, right?
trivial or useless, but the interesting thing is that all this information from here to here must go through this tiny, small feature space. So all the necessary information which is necessary to reproduce the image of Daniel can be put into this small space. And this is actually pretty useful, as we see later. And we can also do funny things with them. So we can, for example, exchange this left and the right part, the encoder and the decoder of this architecture, with those trained for another person. And you can see, well, you put Daniel in, and you get me out. And this is what we use for our deepfakes, which you can also check out down below. So yeah, that's possible with CNNs. So what else is possible?
So now we provided a few of the demos, how AI actually sees. And in this kind of example, we have similar before, we have the output layer that it classifies something. The model is trained on arbitrarily things, so it can classify a lot of different kind of stuff. Sometimes not too good, sometimes, but like what we're actually doing is running everything on this laptop here. So you only have to be able to run the small models without that huge of a GPU, except he has actually an M4, so it's pretty fast right now. But we had it also running on like a smaller laptop. This runs on CPU, so it's fine. Yeah, and what it detects is you can see some kind of percentages, and this could be like it detects suits and windows and stuff like this. But essentially, what we want to show with this is you can run everything on your own hardware. This is also what could happen, like for example, if you have like surveillance cameras, and like the computer vision itself is pretty small because of all the CNNs compared to like normal neural networks are pretty small because you only train the kernels and not like the whole dense layers. Too mathematical, I know. But yeah, and this is like a task that you can do with computer vision. What else can we do?
So, well, this simple classification is, well, can be quite useful if it's clear what's in the image. However, the information might get useless if you have lots of images, lots of items in the image, and, well, you get weird information. So another thing which we can do is object detection. And as you can see here, it actually places boxes around the items on the image. So now I'm trying this, but usually it somehow works.
Sometimes, yeah.
Okay, you can then see, okay, there's obviously a person and sometimes a bottle in this picture. And this wouldn't be possible with plain classification because you would simply get overall probabilities for the entire image. And this can get really ambiguous if you have multiple items in the image. So object detection is actually an advancement from this simple classification which we've seen before, but the base architecture is again CNNs, this time trained on object detection. So
yeah,
what else?
But maybe we want to know a little bit more about the image, because now we have the bounding boxes, but we still don't know really where exactly the items are. And this is where segmentation come into play. And here, if you think about the slide before, which we had like the compressed items, here, of course, we kind of want to classify every pixel of the image. So the output will have a similar dimension, except that, of course, we only currently classify the foreground from the background, so we don't have the 3 channels in the end. But yeah, what you're actually doing is segmenting every pixel if it belongs to the image, or like to the foreground, I mean, or not. And this is what segmentation does, or in this kind of binary segmentation, you can also do like object segmentation, where you segment specific objects or separate objects from one another. And this way, the AI or the computer can kind of separate things, so it understands what's actually in the room. And here, of course, this is pretty simple to have like foreground, background. But if you have like items that you really want to detect, maybe in some machineries or stuff like this, this can help actually also to autonomously drive. For example, if you think about road detection, the car must know where actually the road is and not just vaguely. So this has to be pretty good. And this is some task that is where also computer vision comes into play.
Okay. Last demo in this section is, can you see it already? Not yet. Okay, yeah, that's the point where you see that this is actually live. Now it works. Great.
Yeah.
So what we see here is a landmark detection of my face. So another application of CNNs, I can use this to track my mouth, my lip movements, my eyes, my facial expressions. And this can also be used for all sorts of things. So in a more funny way, we use it for our deepfakes again in order to make it look more natural, because this autoencoder swap, which we've shown earlier, that might use, but some features actually do get lost. For example, if you move your face simply, and we can grab this kind of information, which models like these, where we put landmarks on the face and track them. So another application. So, but what's the cool thing about
the cool thing is you can do everything yourself. I mean, normally you wouldn't put code here, but this is actually the whole thing you need for running all kinds of models that are pretty simple and run on CPU. And for example, one of the items is YOLO, which we also show downstairs, where it's pretty simple to track items, detect items, put bounding boxes around them, and just play around with all the kinds of computer vision items. And one other model there is MediaPipe, and this is what you have seen in the last demo, where you really are able to detect facial landmarks, or there's also pose detection. You can kind of, we built a showcase before where you had like a dancing robot where you need to pose, and this is the library we can use for detecting poses. And yeah, for this is still like it's a few lines of code, and then you have everything running. You don't need to train it yourself. You can just use it. And this is what we also want to tell you in this talk. It's pretty simple to use computer vision yourself, and if you're interested in, it's a small step to start. But let's switch over to something that is completely different from just recognizing image, because now we are only able to recognize what's inside, or the AI is able to recognize what's inside of the image. But what if we want to modify it? So we kind of are in a place where we can use the image, put it into some CNN, and are able to say, this is a house or whatever. But what if we want to change something about the house? And this is where like the GenAI comes into play, and GenAI is able to generate new content. And of course, everyone knows LLMs, so we start with LLMs to tell you a little bit more about how to modify, how to kind of reimagine the content that you're actually seeing.
Yeah, so LLMs, how do they work? The thing is, you put text in and you could get text out. So you can put in the best software is written by, and the LLM completes this sentence by predicting the next token, or more precisely, it predicts the probability of the next token. So to the best software written by, according to our nice model here.
This is still statistics, so if the statistics say AI is writing the best code, then this has to be true, right? Well, no, it's only probabilities, but the AI, of course, will want to be the best.
So, well, according to our nice LLM here, the most likely completion to the best software is written by is AI, and, well, less likely developers. Well, it might be opinionated, but it's the AI. Okay, that's text to text. Now, we are here in a computer vision talk, so what about images then? And in fact, there are things like vision language models, which don't only take text as an input, but also an image, which you can use to condition the response, which are the next tokens. And this gives the possibility to actually ask questions about an image. So you can now ask the VLM to identify the object. And based on the image input, it will now return the probabilities for the next token, which is Apple in this case. So this is what VLMs do. Completion of text conditioned on image input. And in fact, this idea actually allows us to fulfill more generic tasks than we have seen them before when talking about CNNs. So when talking about CNNs, we had models which were specifically trained on rather narrow tasks like classification, object detection, segmentation, and so on. Now we can ask all kinds of questions on a picture. And again, for this, we also have a showcase down below, which is Malos and a machine-regulated logic operating system. And the idea behind it is that in our lab, we sometimes have trouble with things like cleanliness. So we thought, why not setting it up and letting a VLM, which of course data safety and so on, runs on our own cluster, looks at the image and in a way answers these requirements, answers to those requirements, which says, well, no heads, no moustache, well, specific rules.
Except in November, then you have to have a moustache.
You can always change.
That's the only rule.
Yeah. And of course, more seriously, no open fire, clean room. And what Malos does, it has in its interior working a VLM which interacts agentically with an LLM in order to produce output, which we then let it distribute via a text-to-speech model. So it actually talks to you if you do something wrong.
In a more or less nice way, of course.
And, well, that's an example how VLMs can be applied, maybe a bit dystopic, but still. And, well, you can also check this out later on in our expo area. So now we have understood or seen that there are also models which understand images and which can answer questions on those images. But Daniel already promised it. We will also talk
we
about...
don't want to do more about like text output. Text output, everybody does that. Let's do more about images. And images is like we switch the image input to the image output, and what do we get? The text to image. So we have a text input and we have an image output. And now the idea, of course, is what do we actually have to do to feed in stuff like, an example, a red apple to get to a red apple. And this is where the text to image comes into play. And the whole idea behind this is like you have something like a drawing. Sorry. You have something like a drawing. Can you play? Sorry, this. Maybe then let's to the next slide. You have like an iterative way of drawing something. So if you think about the idea of drawing, so you start at some vague figures. You start at, for example, like the structure of an apple, and the more and more you continue to draw, the more and more details you will add. And this is like, I don't know, like when was the last time you draw? I wouldn't start at like the finer details because I wouldn't even know what like is inside the image. And the same way is how like it's called denoising diffusion in this field. This is the same way how AI does that. So you see below. So this is like the human does that. We go from a simple structure to more detailed output. And the AI is doing this similar way. You start at some kind of noisy figures of vague shape, and the more and more you progress, or the more and more it progresses, the more and more clearer the details are added, and the more and more clearer the output result will be. And the whole process we demonstrated in the next slide. So we start at some time step t0, so we start at the beginning. We have this image of an apple, and the whole thing here is that we add some noise to the apple. So we have this apple, add some noise, and then we get a more and more noisier apple out. And of course, if we go this way, it's pretty simple. You just add some random noise in, and then you have a more and more noisier apple. This is not what we actually have. Like, that's just not complicated, because if we put in a banana, of course, we can also merge apples and bananas. What do we do with it, actually? And the whole trick here is to go not this way, but drag the slider in the other way. We want to go actually from a noised image back to a denoised image. So what we are actually doing is learning how to predict noise in an image to get a less noisier image. So if we have something like a noise, or like noise sampled from a distribution to be detailed, we will sample only how much noise is in there, and not actually what actually is inside the image, only to like kind of noise prediction in the end. And
yes,
the whole thing, of course, this is the forward way, and now we have to go backwards. And how are we doing that?
Exactly. So now we want to give a description of what our model should, in the end, return or draw or produce or generate. And this is our starting point. We say we want to see a red apple. And now we have this model which has previously been actually trained on noising images. And it knows how to noise an image which has a red apple in it. So we tell them, well, here's some noise. This used to be an image of a red apple. Now denoise it. You know how you did that. But, well, in fact, we cheated kind of way, because this is simply random noise. It actually has nothing to do with the apple. But nevertheless, the model thinks that this used to be an apple, and it predicts the noise which should have been used to noise that image, and we can now subtract these noises. And all of a sudden, an apple appears.
Of course, for this to work, the model has to be trained beforehand. So it's
Yeah,
not
for
that we're removing the noise without having learned something. If you remove noise from like the starting point, you will get noise out or anything else. This can happen, but in the end, you have to train the model again, and then you get this output because the model knows how a red apple should look like.
Exactly. So we can tell them denoise this noise and get any kind of image which we ask for. So let's try this out in live, how this actually looks like. So again, a live demo takes a couple of seconds. But what we want to do now is to generate a fantasy landscape with mountains and a river. And now we can see here, we start with noise. We predict the noise which we imagine to have produced this final noisy image, subtract it, and get an actual image. So,
and of course, we don't do that for one step, because if you think about the drawing again, you want to draw the image in one step. This is not possible because it's too hard to do everything at the first try. That's why we do it step by step, because then we know the more, like if we have learned to remove noise at every time step, we know how this looks like, so that we add details in later step, so we can kind of fine grain or get to the direction we actually want. And this is also why if you're using these models, if you put more time step, the more like cleaner your output will become. But of course, you don't want to do it like a lot of times because it takes more time. So in general, you have like a good middle way to balance this.
But we cannot only generate totally new images. We can also in-paint images and say we want to change the background of this image of an apple. And instead of starting with a fully noisy image, we create a mask of our apple, and we mask the area which we do not want to change, in case this apple. And well, with this we can, of course, remove the background, but we can also put noise in it, and now denoise this noisy section. However, the model understands the integrity of the image. It knows there's an apple in there, so it's able to create a background which still looks like the background of this apple, so it can create shadows, like here.
Who has never seen an apple on the beach?
Yeah. And this is the way how in-painting works. So you don't always have to generate a totally new image. You can also start with an existing image and only regenerate parts of it. So now we've talked a bit, there's a model, but how does this model actually look like, Daniel?
So in general, what we have seen before, because we made a little bit of a trick here, if we would run a full denoising model on this, or diffusion model on this PC, it's really computationally exhaustive. We don't want to do this, so we did a little trick. We put everything in the so-called latent space or feature space, which we have seen before. And if we recap, we have seen, if we put my image, and maybe click you, we put my image inside the process of kind of reconstructing the image, so the autoencoder, which we have seen before. If we use this kind of technique, we have something here in the middle that is really, really strong if you trained it long and good enough. We can do this for my picture, of course, but we can also do this for the apple. So we put the apple in, and we can do this for everything. And in the end, you have like a model that is really able to understand what is inside the image. And then if you have a good enough representation, you can use this to or use this for denoising. So you're not doing the diffusion in like pixel space, as we call it. You don't do it pixel by pixel, because then the machine would like crash, I think. But you will do this in kind of a latent space, so in the feature space. You're only using the information that the network actually has learned. And this will look like the following. So in the end, the latent space knows, oh, maybe the apple is round, maybe it has a stem. And yeah, if you have all kinds of information, then it can take this information, or their apple is red, and all kinds of information, then you can do the diffusion process in this space. So what you're actually not doing is the pixel space here, but you're replacing this. So here you see the denoising part, everything in pixel space, but you replace this with the next, with the kind of idea of what actually is inside the image. So the denoising, everything happens in this space. So you know the apple is round, it has a stem, it is red, and all kinds of information is included in the space already. You're doing the reverse or adding noise process in this latent representation. And this way you will save a lot of GPU power, I can tell you. So to make it working on, for example, his machine. But otherwise, previously we had models that work on pixel space, but only OpenAI could actually train this and run it. But nowadays, everyone can run this at home, at their own laptop. Sometimes you need a GPU, all kinds of things already exist without GPU usage, but you can use diffusion yourself. And
Yeah,
if we have like one item we showcase is the AI photo booth. And this is actually using the diffusion technique to create something magical.
Yeah, exactly. So another showcase, which we have down below, to show what to do, what we can actually do with denoising and image generation models. So the AI photo booth, you can go there, make a photo of yourself, and say, I want to be at a barbecue, or maybe somewhere else, and you get a picture of yourself at a barbecue. So what's behind it? It's, in this case, again, a CNN, which we know from the beginning of our presentation, in order to look at the starting image which you've made of yourself, which you took of yourself, to recognize where your face actually is. Together with the text input, you can select which scene you want to be in. This is fed to a text-to-image model, a denoising model, which we've learned, which we've seen earlier, and together they generate this new image of you at a barbecue, for example. And yeah, check it out yourself. You can simply take a photo of yourself, and then you can take home your actual photo.
Hopefully
if you like
it will not creep anyone out.
Yeah, we have a printer for that. So if you like, you can take home one. All right, Daniel.
So,
what have we learned today?
What have we learned today? So what we have seen is AI is able to see you. So AI is able to see you. So if we, for example, take the image of Leonard again, AI could detect all kinds of information inside the image, for example, the face mask. It knows actually what is happening inside the image. And even more if you use like VLMs to kind of control what is happening inside our room, what is happening everywhere. We are able, or the AI is able to understand what is happening, what it can see, so it is able to see you. But what's also happening, AI is able to modify you. So modification can look like, for example, the deepfake, which we have shown before, that we can replace the face of Leonard with the face of me, for example, and that the AI is able to kind of modify the content and actually sees. So, of course, we have to be aware of that. And the last thing is, we cannot only modify the content, but we can totally reimagine the content. So if we have the photo of Leonard again, with diffusion models, if you fine-tune them, for example, you can reimagine Leonard in a whole nother way. And this is actually what we wanted to show you today, that the AI is able to understand everything. The AI can modify content, and you can also do lots of new cool stuff with it.
Yeah. And with this, thank you for being with us in this talk, and make sure to check out the showcases on your own. Thank you very much.
Of course, we have normal pictures too.
Well, thank you guys. Thank you so much. We have now some time for questions that you might have. So either in person here in this room or on Zoom as well. So, yeah.
So all the things you showed, were they frame by frame? Or, for example, for the object detection and the segmentation, is there some learning from the picture before and or the time before and the time after?
So what we've shown today was actually frame by frame, and for the CNNs, it also works frame by frame pretty well. So you could also see when I showed the bottle there, sometimes it recognizes it, sometimes it recognizes it, sometimes not. So that was actually on a frame by frame basis, yeah.
So of course, to have a bit more, if you know that you have multiple frames, normally you can also go ahead and take more information than the segmentation, for example, would be better. But yeah.
Hi, thanks a lot for the talk. My question is about the feature space. So like, for example, on the slide where you had an apple and a detection that it is round, that it has a stem, that it is red, I was wondering if there is a way to tell that the CNN is actually detecting those features.
That's a good question. I mean, you cannot really be able to tell what actually is happening, but you are able to kind of encode and decode again if it understands what actually you had as a task. So the feature space itself, kind of they showed that this is the representation is good enough to reproduce kind of the original image itself. So this is what actually all kinds of research got into. And actually, like where I think Stable Diffusion was the first that kind of showed, if you take the pixel space and replace it with the latent space, you get enough information for this diffusion process. But if you want to really visualize it, I think that's more complicated there.
I see. So it is functional in the sense that it stores essential information that is sufficient to reproduce the image, but we can't really reason about it.
Yeah, and of course, if you
like
encode something, sometimes you lose information that you as a human would kind of miss inside the image. And a lot of like items that, or previously we had problems with, for example, fingers and counting and stuff like this. Everything is getting solved now, and the whole diffusion process now looks different than what it was actually a few years back. But yeah, so you can miss a few things, and sometimes the visual quality or the output will look a little bit strange to the human perception. But this will get better and better, and if you train, of course, large models, then you can kind of get close to what you actually perceive.
I see. Thanks.
Right. Do we have more questions? If not, maybe I have a question. Because during the talk, you emphasized a lot that most of the things you can now run also on your laptop yourself. And then you alluded a bit to that sometimes you also need to train and fine-tune stuff. So maybe can you give like a little overview of what the possibilities are for me, not only to run stuff, but also maybe to fine-tune things to fit my own needs and purposes?
So in general, of course, because we kind of the innovation hacking, we have like a lot of GPU power behind it. So in general, we train on GPUs because it's faster. But if you have like, for example, the M1 to M4 Max, they have also the ability to run or train a little, a little bit higher parametric models, but like for computer vision model, a CNN you can really easily train on your CPU because, of course, also like something we showed with YOLO and MediaPipe, you can fine-tune them with your own data on your laptop. This is pretty easy. But if you, for example, look at the Muppet or the puppets I generated, I fine-tuned it on like RTX 4090, so you need a little bit more compute to actually do that. But like for the smaller models, CNNs is pretty easy to do.
But
normally.
the cool thing is you don't always need to train your own models. There are already lots of models out there which you can use out of the box, which are pre-trained and probably pretty good for many applications. So these classification or segmentation, object detection models which we demoed here are actually pre-trained. So if you don't have specific needs, just go with a pre-trained model and you don't have to go through all that struggle. And those models are now fairly small and many machines are capable, or many consumer-grade hardware is actually capable to run those models.
And you need to look at, if you have inference time, normally there are optimized ways to run models on in inference time. So in the time when you actually want to classify compared to training, because training is mostly more exhaustive than doing like only the sampling process.
All right, thank you.
There's another question?
I have rather a complex question. So imagine you have the challenge that you want to exchange the part of an image, but you cannot identify the part with the CNN. Let's say, imagine an image with a glass of Scotch whiskey, and you want to change the color of the whiskey to red. So then you won't be identified to identify a mask for the whiskey because, well, there's a model for it.
Yeah.
Is this a task that can be solved with current technology?
I mean, normally, like if you look at newer models, they are able to kind of replace items with the diffusion model itself. So you kind of can prompt it to remove items inside the image. And if you have a large enough, for example, they use VL architectures or vision language architectures in the back end, so are even more powerful than only doing like an embedding, which we have shown before. So they're able to kind of understand better what is actually happening inside the image. And then you wouldn't need the CNN in the first place. You could now, for example, one of the items, the model that I trained with the puppets, this is actually able to understand what it needs to change, but of course it needs to detect it first. So if it's too small, maybe this is difficult, of course, but like if the model can understand it, this is an easy task.
Does it mean that vision language models can also be used for segmentation?
Yes.
Yes.
No way.
Yes. No, they can. And also, the funny thing is, also for diffusion models, they found out that you can use diffusion models with a little thing extra on top for segmentation too. But yeah, it gets complicated if you step in there. Because if you have a large enough model, then everything is like only adaptation.
You said you learned the Muppet thing yourself on the 4090. How long did that take?
2 to 3 hours.
Okay, thank you.
All right, the time for questions is up now. So if you have more questions, I'm sure you can find our two speakers down there at the showcase space. Make sure to check them out for yourself, and let's thank our speakers again.
Thank you.